Yeah, now we deal with power. What power generally we mean is, if at all we are lifting a weightlifting, generally we say how much power do you have. If at all we are having an arm wrestling, they say how much wrestling you are having. But generally in physics we don't define like that. The definition of power can be defined as time rate at which power is done or energy is transferred. So the power can be defined as in the many terms. Average power of the force is defined as ratio of work done to the total time. So this will be equal to the power average is equal to the work done by the time. And also we had instantaneous power. What instantaneous power is? Limiting value of average power as time interval approaches 0, that is at a particular instance of time, so that is taken as instantaneous power. Instantaneous power is equal to dw by dt. So we can express this as dw, work done by a force F for a displacement dr, is equal to dw is equal to d of F into r. As work is equal to F into r, we are defining dw is equal to the d of F into r. As force is constant in this situation, we take the instantaneous displacement of the particle, that is dr. That's why we will be getting dw is equal to F into dr. Now for the instantaneous power we get P instantaneous is equal to the P dw by dt, that is equal to F into dr by dt. We know for the velocity dr by dt is equal to the velocity. So P instantaneous is equal to the force into velocity. Here the v is the instantaneous velocity of the particle. Yeah, now we deal with the chapter collisions. In physics we study motion. At the same time we try to discover physical quantities which do not change in a physical process. The laws of momentum and energy conservation are the typical examples of them. Consider two masses m1 and m2 which are moving with a speeds v1I and the other particle v2 is at rest. So now the first particle gets in contact with the second particle and the both particles move in a different directions compared to the second initial positions. So this is called a collision. Generally in physics terms we define this as, if there is an impact of one body on another, then there is said to be a collision. So now basically the collisions are of many types. It can be in one-dimensional collision or two-dimensional collision. Based on conservation of energy and momentum, laws of momentum, we define collisions into two categories. One is elastic collision and the other is inelastic collision. In elastic collision, the linear momentum and energy both are conserved. Generally in a particular collision, both momentum and energy is conserved in the elastic collision, and when the energy is non-conserved, then it is said to be an inelastic collision. The fact we should remember is, in every collision, laws of momentum is always conserved. We can further go into deep, like one can argue this as follows: when two objects collide, mutual impulsive forces acting over the collision time delta t causes a change in the respective momentum. That is, if we take for the particle A, delta p1 is equal to f12 delta t, and for the particle delta p2 is equal to f21 delta t. Here f12 indicates the force exerted by the particle 1 on 2, and for the f21 2 1, it indicates force exerted by the particle 2 on 1. The above conclusion, in every collision we can define in such a way that delta P1 plus delta P2 is equal to 0. The above conclusion is true even though the forces vary in a complex fashion during the collision time delta t. Since the third law is true at every instant, that is Newton's third law is true at every instant, total impulse of the first on the first objects is equal and opposite to that on the second one. We have on the other hand, total kinetic energy of the system is always not conserved, because if at all it is an inelastic collision, the impact and deformation during the collision may generate heat and sound. Part of the initial kinetic energy is transformed into the other forms of energy. A useful way to visualize the deformation during collision in terms of a compressed string. If the spring connecting the two masses regains its original shape without loss in energy, then the initial kinetic energy is equal to the final kinetic energy, but the kinetic energy during the collision time delta t is not constant. Such a collision is known as elastic collision, and such a collision is known as elastic collision because in this case both the energy and the momentum will be conserved. On the other hand, the deformation may not be relieved and two bodies could move together after the collision. A collision in which two particles move together after the collision is called completely inelastic collision. In completely inelastic collision, the bodies stick together and move, so the velocity after the collision will be equal for both bodies. Velocities for both bodies will be equal after collision. The intermediate case, where deformation partly relieved and some of the initial kinetic energy is lost, is more common. These type of problems is in more common, and apparently these sort of collisions we generally say inelastic collision. Basically, when the particles stick together and move, these sort of collisions is perfectly inelastic collision. And if the bodies doesn't stick together, and then it may be said to be the inelastic collision, or else it is said to be inelastic collision where kinetic energy is not being conserved. Now let us deal with the dimensional collisions. First we deal with one-dimensional collision. So in one-dimensional collision, if suppose we consider if the initial velocities and final velocities of both the bodies are along the same straight line, if initial velocities and final velocities of both the bodies are in the same direction or are along the same direction, then it is called one-dimensional collision or head-on collision. Generally in the competitive exams they will be giving head-on collision. Don't be confused with any other collision, it's just a one-dimensional collision. So now let us go to the two-dimensional collision. In two-dimensional collision, what it is like, in the above one-dimensional collision, the body first hits the body and moves in the same direction. But in two-dimensional collision, if suppose we consider body of mass m1 moving with initial velocity u1 hits a body of mass m2 which is at rest u2 is equal to 0. If at all it is a two-dimensional collision, then the body moves in a different directions. If suppose we take this as xy coordinate, it moves in a different directions. So this is said to be a two-dimensional collision. Now just let us deal with the equations of one-dimensional and two-dimensional collision. First we see for one-dimensional collision. Let us consider the collision is an inelastic collision. Let us take a body of mass m1 moving with a velocity u1 towards a body of mass m2 which is at rest u2 is equal to 0. As it is an inelastic collision, both bodies move together once they collide with each other. So according to law of conservation of momentum, we get m1 u1, which is the initial momentum of the system, is equal to the final momentum of the system, which is equal to the m1 plus m2 into v. Thus we get v is equal to m1 u1 by m1 plus m2. So we can get even the loss in kinetic energy due to the inelastic collision. So let's consider that loss in kinetic energy due to the inelastic collision. Due to inelastic collision. So this will be equal to delta Ke, that is equal to half m u1 square, which is the initial kinetic energy of the system, minus half into m1 plus m2 into v square. As this is the combined velocity of both after the collision, we can directly write this as v square. So this finally, after solving, putting the v is equal to m1 u1 by m1 plus m2, we get delta Ke is equal to half into m1 m2 u1 square by m1 plus m2. So let us now consider about the elastic collision, elastic one-dimensional collision. In elastic one-dimensional collision, energy is also being conserved, so we should not take the loss in kinetic energy. Let the initial velocity of the particle be u1 on of mass m1 and the final velocity of mass m1 is v1. After the collision, the velocity will be becoming v1. Let us consider the body of mass m2 with the initial velocity as u2 is equal to 0 and final velocity v2 is, and the final velocity be v2. According to law of conservation of momentum, we get m1 u1 is equal to m1 v1 plus m2 v2. And as it is an elastic collision, according to law of conservation of energy, we get half m1 u1 square is equal to half m1 v1 square plus half m2 v2 square. So by solving these two equations, we will be getting, and by substituting the equations of 1 and 2, we will be getting v1 is equal to m1 minus m2 by m1 plus m2 into u1, and v2 is equal to 2m1 u1 by m1 plus m2. So here we just considered the elastic collision in one dimension, and by taking the equations of law of conservation of momentum and law of conservation of energy, we will be getting the final velocities of each body. v1 is equal to m1 minus m2 by m1 plus m2 into u1, and v2 is equal to 2m1 u1 by m1 plus m2. In the above situation, we can have some special cases, like if special cases which we generally will be getting in the competitive exams like JEE Mains or JEE Advanced. If suppose m1 is equal to m2, then the final velocity of the first body will be equal to 0 and the final velocity of the second body will be equal to the initial velocity of the first body. And if suppose m2 is far greater than m1, that is mass of second body is far greater than mass of the first body. So in this case we will be getting m1 is nearly equal to minus u1, that is once after hitting the second body, it just goes back with its initial velocity in the reverse direction, and the final velocity of the second body still remains 0 because mass of the second body is far greater than mass of the first body. Up to now just we have seen the one-dimensional collisions of elastic and inelastic collisions. Now we deal with the two-dimensional collisions of elastic and inelastic collisions. First, suppose a body of mass m1 is moving with a velocity u1 towards a body of mass m2 which is at rest u2 is equal to 0, and after the collision let the bodies move apart in a different directions. Let this be the directions of both the bodies after the collisions, and angle they have been deflected is theta 1 and theta 2. So now it depicts the collision of a moving mass m1 with the stationary mass m2. Linear momentum is conserved in such a collision. Since momentum is a vector, this implies three equations for the three directions x, y, z. As the z direction is same for all the thing, we consider only the xy direction. We are just taking the coordinates of xy. So the x component, by law of conservation of momentum, x components of the bodies is m1 u1 is equal to m1 v1 cos theta plus m2 v2 cos theta. Actually, when the body is moving in this direction with a velocity v1 making an angle theta 1 with the horizontal, then in this direction the velocity component of the first body is v1 cos theta 1 and of the second body is v2 cos theta 2. So in this case the x components we will be getting m1 u1 is equal to m1 v1 cos theta 1 plus m2 v2 cos theta 2. And in a similar way for y component we get, initially in the y component there is no velocity for any of the bodies, so initial momentum on the y component is 0, that is equal to m1 v1 sin theta 1 minus m2 v2 sin theta 2. So naming these equations as equation 1 and 2. So by getting these two equations and considering it as inelastic collision or elastic collision, we solve the two-dimensional collision problems. One knows m1, m2, v1 in most of the situations. There are thus four unknowns v1, v2, theta 1, theta 2 and only two equations. So they should be giving any one of the quantities like theta 1, theta 2 or v1 and v2. So if at all we consider theta 1 is equal to theta 2 is equal to 0, it will be a elastic collision in one-dimensional collision, and directly we can conserve the kinetic energy. And if at all it is not equal to 0, then we should take each individual component and substitute the kinetic energies of each body. We obtain an additional equation that still leaves us one equation short. At least one of the four unknowns now definitely should be given to solve the questions of this type. Yeah, now we can just summarize the chapter. Basically in this chapter we mainly deals with work energy theorem, law of conservation of energy, collisions, which is 1D collisions and 2D collisions. Basically in any GE problems, generally most of the problem deals with law of conservation of energy and work energy theorem. Work energy theorem, the questions can be asked in a different way. Basically it can be a conservative work done or the non-conservative work done. Anyone solving those sort of problems should be careful regarding how many conservative forces and non-conservative forces are being dealt with. So that's it for this chapter. Next